So yeah, I'm Daniel. I'm a principal engineer at Disney Streaming, and yeah, we're hiring. So if you want to work on stuff, I actually work mostly on like cloud architecture things these days, and so this type of thing is like much more interesting and much more engaging overall. So what I wanted to talk about is I wanted to talk about three things really, and all of these things boil down to how we can do a better job of designing and implementing applications that run at an extremely high scale with extremely high efficiency. And as a real-world motivation, before I get into the talk, just to motivate what I am actually going to present, this is a paper that you obviously cannot read, but the URL is in the slide notes, and I'll try to tweet this out or something like that to make sure that people have it. It's a paper from the University of Helsinki from 2019. This is the carrot to this talk, okay? Because what they did in this paper is they took production memcached and they modified the implementation to take into account some of the things that I'm talking about here today, and they improved the tail latencies by 71%. So over production memcached, they improved the tail latencies by 71%. That is an insane performance improvement. Like, I will take that any day of the week. Now, obviously, memcache is written in C. It's very confined space. It's probably the idealized use case for these types of optimizations that I'm going to be talking about. So in practice on the JVM, I generally see more like 30 to 50%. But still, 30 to 50% tail latency reductions, like almost for free, why wouldn't you want that? Like, that's just money in the bank. So what I'm going to be talking about to actually achieve this is really three things, okay? Concurrency, asynchronous I/O, and timers. And traditionally, these have been seen as three very separate domains, particularly on the JVM. You kind of see them as three things, you plug them together, and you try to make them interact. But really, ultimately, they are fundamentally almost one thing. And what this talk is kind of going into is the benefits that you can get if you do bring them closer and closer together, and why it is that they are in fact the same thing. Because what we're going to be looking at is how they work under the surface, okay? One of the big ideas behind this talk is something called mechanical sympathy. So if you talk to folks at Amazon a lot, they sort of like bring this up. And really it's the idea that like if we understand the sort of stack underneath us, we don't necessarily have to be able to build it all from scratch and understand it at extremely deep detail, but by understanding it at least a little bit, we can write programs and engineer software that is better suited for the underlying implementation. It's sort of sympathetic to the machine. Here's a quick example of something that is not mechanical sympathy, right? So like you've probably seen this, and some sort of like smart aleck on your team goes in and like modifies the code, so instead of x times 4, it does a left shift by 2. This is not mechanical sympathy because every compiler will do this for you. So this is just kind of pointless obfuscation. This, however, this is mechanical sympathy, where we know because of the way that garbage collectors work, because of the way that memory pages and cache lines are sized, because of the way the arithmetic operations work when you're accessing arrays, the powers of 2 are just more efficient, okay? So rather than doing a power of 10 or some random number that we throw in here, we use a power of 2, and that's going to make our program run faster. This is mechanical sympathy. Now, we didn't have to know how to implement a garbage collector or how to actually solder memory onto a motherboard to be able to actually make this determination. We just had to have a little bit of understanding of how the machine works. Now, quick disclaimer. First off, I'm not a hardware engineer, so I'm going to be talking about hardware things, which is really funny. But like, we're going to be talking about a very simplified version of Linux, a very simplified archetype of hardware. The actual reality is more complex than this. We are glossing over a lot of details, but not details that actually matter in a meaningful way to the outcome of this talk. Other operating systems and architectures, most notably Windows and ARM, are quite different, but again, not in ways that affect our bottom line conclusion. So really, everything that you learn here hopefully is pretty applicable to anything you do, even if you're on some sort of like fancy Apple ARM thing doodle that is maybe the future. All right, so with that out of the way, we have a lot of ground to cover, and we're going to start with the hardware. So why start with the hardware? Well, the hardware is important because everything we do ultimately comes down to real hardware in the end, okay? If the hardware can't do something, we can't do it either. I cannot write a program that actually launches the missiles, much to the disappointment of Haskell enthusiasts everywhere, right? And the reason I can't write a program which actually launches the missiles is there is no missile launcher connected to my computer, Okay? All I can do is what the computer allows me to do. And it's very important to understand that like when you actually take apart the machine a little bit and peel apart the layers of abstractions, at the end of the day, it's really just electrons in the wires. And electrons are physical things that have physical properties, including propagation delay, right? They move at roughly the speed of light. And the speed of light is not instantaneous. And as it turns out, that actually starts to matter big time, especially at scale. We think of it a lot when we're thinking about like transatlantic network connections and things like that, but it turns out it also matters within an individual box itself, like within an individual hardware unit. And because of this, space and the orientation of space really matters. And as it turns out, if we think very carefully about this stuff, this actually impacts all of the optimization space, all of the performance characteristics of the applications that we write above this layer. So here's where it starts. This is a die shot of the AMD Cezanne architecture, which is the underlying architecture behind the most recent generation of AMD Ryzen chips. And it's an ultraviolet shot blown up like a million times. And the colored sections, which are probably very, very difficult to read, and they're not really intended to, there's a lot of them here. But the really important ones to look at are the ones that are kind of like teal. Those are the compute units, like the actual CPU cores. Okay, then you've got dark blue, which is the L2 cache, and then you've got purple, which is the L3 cache. And there's a bunch of other stuff that really doesn't matter. But like those things are the things that we're mostly going to be talking about today. And you notice how like they're really close together, they're very tightly intertwined, and then there's a bunch of stuff around it. This is also very, 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 very tiny. Okay, so I've inflated this image enormously, right? This whole thing actually fits on the tip of your finger. And then it gets wrapped up inside this enclosure, which has a bunch of like dye and like heat dissipation and things like that, which is also still relatively small. You put that under a heatsink, and then you slap that onto a motherboard, which is way the hell away from where the actual main memory is. Okay, that's the picture I want you to have in mind. It's like I kind of inflated this really, really huge this thing really, really huge, but it's actually tiny right in the middle of this square. And that is the difference between accessing memory that is in the L1, L2, or L3 cache layers versus accessing memory that is actually in main memory. So have that picture in your mind. Remember that the electrons have to walk over these whole paths like hundreds of millions of times, like back and forth and back and forth and back and forth. This physical arrangement gives rise to what is the single most important caching hierarchy in all of computing, which is this right here. And this exists inside of every physical hardware, right? So fundamentally, you have the CPU, which is a bunch of compute units. And these compute units can operate on data that is in registers, and those registers get populated from data that's in main memory. And when you access data in main memory, you access it through these cache layers because these cache layers are so much closer to the compute units, as we just saw, and therefore they're much, much, much faster. And there's all these assumptions that the CPU builds around how we're going to access memory that it uses to try to make this as fast as possible. Specifically, the assumption of sort of like proximity, right? So if you're accessing offset 0 in memory, the CPU is going to assume that you're also going to access offset 1 and probably offset 2 a little bit later, so it pulls all of them into the cache hierarchy, which means in turn that when you're writing programs, if you can live within this assumption and like obey that assumption, then the CPU is going to do a very, very good job of optimizing your code for you. And as it turns out, this is where the majority of that 71% comes from that I referenced at the beginning. If you violate this assumption a lot, and most people actually do, then you sort of blow this away, and it's as if you sort of didn't even have the cache hierarchy in the first place, and your pathways have to traverse all the way out of the CPU to the main memory, like back and forth and back and forth and back and forth. And that's very, very slow. So have that picture in your mind. And while you have that picture in your mind, let's look at some more details of how the CPU works, okay? Because this also affects some other things. So inside of the CPU, there are registers, like I said. An AMD CPU has about 80 of these things. And there's a lot of different types of registers inside of there, but the most important ones are the ones which represent the program counter, the interrupt register, and the data registers. Okay, so I have those right here. There's more, like I said, glossing over details, but these are the really important ones. And these are important because of how the CPU works. So the compute units basically execute one-ish instruction at a time. Like, I'm ignoring hyperthreading here because it just kind of makes things really complicated, but like, you know, one-ish instruction at a time. And the program counter points to the offset into the program, like a line number, into the assembly code offset. The instructions access data in registers. Instructions can load data into registers through the cache from main memory. And the interrupts preempt the next instruction. So the interrupt and the program counter kind of play off of each other. Interrupt is a little bit like a jump or a go-to or something like that. Interrupts come from hardware. So this is like your I/O bus, PCIe, like maybe your timers, like stuff like that. That's what triggers interrupts in the CPU. All these things come from the hardware. These are the primitives that we have to work with. So again, really important thing to understand here. You didn't see anything about thread. You didn't see anything about like preemption aside from like the interrupt thing. You didn't see anything about like scheduling or anything like that. So like these are the primitives that the hardware is providing us. So what we have to do now is like build our teetering tower of Pisa of abstraction on top of this so we can get all the way up into threads and thread pools and socket groups and all sorts of other randomness that we have at the high level. And the very, very first layer that has to do this is the kernel. So how does the kernel work? Well, the kernel is responsible for taking this and giving us the abstraction of a thread. So what is a thread? Well, to the kernel, a thread is nothing more than a bundle of register values. So the idea is basically, for every single thread, there's going to be a bunch of values that were in the CPU register when that thread was active on the core. And it sort of grabs all of those values, puts them into memory, and then associates them with a thread, and then those you can have as many threads as you want. When the thread is inactive, it's in this state. When it's active, they actually put it on the core. So every single core, in turn, has multiple threads associated with it. Each one basically has its own independent task queue, right, thread queue, that represents sort of the next threads that need to be scheduled. And it has its own schedule function that runs local to that core. Whenever a core is idle, it will work steal from the other ones. Okay, so this is basically how work leveling works inside of a CPU, or inside of a kernel. The schedule function works in the following way. So first, when it runs, it checks to see if the current time slice is expired. We'll talk more about this in a minute, but it's very important. If the time slice is expired, select the next thread from the priority queue that's local to that core. If that thread is ready, context switch it in, which basically means take all of the registers from the CPU right now, copy them out into memory, so make a new sort of thread bundle out of that, insert the old thread into the queue at the lowest weight, the one that you just copied out. Copy the new registers in, and then allow the CPU to resume. If the next thread is not ready, maybe it's blocked, waiting on an interrupt or something like that, increase its weight so that when it does become ready, we're definitely going to pick it up, and then proceed with the next thread all the way through the task queue, okay? So this is how the schedule function works. And every time you call the schedule function in the kernel, this is kind of what it's going to go through and do with the threads. Context switching, which is that thing that happens when it decides it needs to move the thread off, is actually a very expensive operation. So this is actually kind of an important picture to have in your head. Like, this is not cheap in any way. So to start, like, copying all the registers off of the CPU is a relatively expensive thing to do. Also, the program counter moves around. So you have this effectively like a go-to inside of the kernel, which sort of dumps the pipelining and like all these other things that you want to have happen inside of your CPU just kind of fall apart when you do this. So all your speculative execution, et cetera, et cetera. With many outstanding threads, okay, so lots of these things floating around, very few of them will share memory. So remember that cache hierarchy that we set up earlier, where the CPU is making the assumption that, well, if you access offset 0, you're probably going to access offset 1. Well, that doesn't apply if you've got threads constantly switching in and out, because different threads will probably access very different segments of memory. So now you're defeating the optimization assumption that the CPU is making, because every time a new thread comes in, you have to blow away all of those cache layers and start from scratch. The more often you do this, the worse it is. You've invalidated the cache hierarchy, context switching is bad, et cetera, et cetera, et cetera. This is one of the reasons that having a lot of threads on the CPU is really super bad. The other reason is time slices, okay? So time slices are like basically this idea that every thread gets a percentage of the available time on the core. And the kernel is going to try to be very fair about this. Time is determined by the hardware clock, and the more threads that you have outstanding, the less time each one gets. So it will actually take time away from your threads just by having extra ones. And when a thread is blocked, it still counts against this budget. So having a lot of blocked threads means your active threads actually get interrupted more often, despite the fact that the blocked threads aren't ready. So these blocked threads are not free. Like they're very, very, very expensive, and they make the core really bad. So we can illustrate this graphically, right? So here's a situation where we have 2 active threads that are actually doing work and 0 blocked threads. So in this situation, the first thread runs, and then the second thread runs, and then you sort of go back and forth, and that's great. Now here, we have the same number of active threads, but we have 8 blocked threads. So the 2 active threads still run for about the same amount of time, but they're getting interrupted and swapped out in between. They have much shorter slices, which means that we're blowing away the cache hierarchy that more often. We're sort of jumping around. We get less speculative execution. Everything is bad about this, okay? So when you hear people say, oh, have fewer blocked threads, or like have fewer threads in general, and they just kind of like give that blanket advice, this is a huge part of why. A huge part of why. And again, remember, that 71% tail latency thing, a lot of it comes from stuff like this. Final sidebar, since we tend to live on the JVM actually makes this even worse because threads are GC roots. So when the garbage collector runs, it actually has to traverse from every single thread, and the more threads you have, the longer it takes. This is why when you have an application that has a thread leak in production, usually the first symptom is your garbage collector pause times just kind of skyrocket, right? When you see that happen, you probably have a zillion threads. Also, JVM tooling around threads is like super, super, super naive. This is one of the challenges of Project Loom, by the way, because like you have IDEs that just try to build like these giant drop-down lists of like 10 million threads. It's also like, frameworks and other things like that don't do particularly well. Fixed thread pool is very, very commonly used, and it's terrible. So there's lots of stuff like this. This is really bad. Okay. So we've gone through from the hardware up through the kernel, like kind of looked at the way that threads work, and this is the abstraction that kind of gives us fundamental concurrency on the JVM and really kind of in any system. I also want to look at how asynchronous I/O works. Like how does it actually function in the system, and we'll see how these things kind of come together, okay? So asynchronous I/O. So as we've said, threads are this very, very heavyweight thing. Having a lot of them is really bad, and having blocked threads is like not really any better, okay? This is a problem because anytime we do I/O, whether it be network or disk or whatever it happens to be, that's going to require that we wait for something. Because again, sort of physics, right? We send electrons over here, it takes time for them to come back even if there were no processing time involved. So what do, right? Like how do we actually handle this? Well, the idea behind async I/O is rather than having every single thread wait for its own I/O operations, why not just have one thread do the waiting on behalf of all of the others? So the other threads can just kind of proceed forward with their work, and you waste one thread on blocking while the other ones do their thing. Graphically, it kind of looks like this, right? So here we've got 3 threads, and they're all doing their blocking I/O, and they have these gaps in them while they're waiting for stuff to come back. If you do this using a standard async I/O process, you would have a 4th thread, which just kind of does the blocking on behalf of the others, and then you have to invent new primary colors to figure out, like, fill the space in the other threads of all the extra time you have created. Basically, we created a lot of efficiency here. Those gaps are now filled by actual work, and the callbacks sort of represent the continuations on this. It's more complicated, but it does work. And the way this actually functions in the kernel, if you're not using some sort of like high-level API, but you're actually like getting down into the weeds of how it's implemented, is this. This is the ePOL API, which I'm going to guess that most of us don't read C fluently, so I translated it into Scala. This is the Scala version of the same API, basically. And it's a really simple idea, right? Like, make yourself an ePOL. You can have as many of these as you want. They're sort of bounded by file handles. And when you have an ePOL, you can add interest in events on a particular file descriptor. So this other file descriptor is maybe a socket or something like that. You're interested in those events. You register for those events. You can add or remove listeners. And then when you're ready, you can wait. And you can block up to a certain timeout, waiting for those events to come back, and the kernel will just report them to you. This is actually the whole asynchronous I/O interface. You probably expected to see something with callbacks or something like that, but like literally callbacks don't exist in async I/O at all. They're an abstraction that we build on top of these things. Usually, the way that we do this is like I showed earlier, where you have this separate thread off on the side that just basically does all of the blocking and has a state machine kind of like this. Like, call the kernel and block, and then did the kernel respond with some events? If not, go back and block some more. If it did respond with events, invoke the callback that you have associated in your map with that particular event. And then if you have more events, just keep doing that until you run out. Otherwise, go back and block. Like the world's simplest state machine whatsoever. It's a very, very, very standard approach on the JVM. This is what Java NIO2 does. This is what Netty does. This is what scheduled executor service does with timers. So basically, scheduled executive service just has a list of timers, and it like sleeps for the minimum time. Same idea as async IO. The problem is it wastes a thread. At least one thread, usually more than that, because for some reason people configure Netty with like 16 threads on an 8-core machine or something like that, right? And the question is, can we do better? Because remember, threads are really, really expensive. And like the more of them we have, contending for resources, bumping things off of CPUs, like triggering work stealing, triggering preemption, the more of that's going on, the worse it gets, right? So can we do better than the current state of the art on the JVM? And unlike every single other problem in computer science, the answer to that question can be found in JavaScript. There is a library called libuv, which is written in C, and it's the library that underlies Node.js. So it's, you can probably think of that as like an archetype of how this works. And the ideas behind this are actually really, really nice. They're not totally unique, but they are a really nice demonstration of it. Libuv has a state machine which kind of looks a little bit more like this. You start by looking at your task queue, okay? And if you have no outstanding tasks, look at your timers. Do you have any outstanding timers? Timers that you would have to wait for. If no, then just block on the kernel. Do the thing that the event dispatcher did, and like ask for any outstanding I/O events. Once you get them, put them into the queue and go back to the beginning. If you did have timers, instead of blocking until I/O events appear, block until either I/O events appear or the timers are ready, and then go back to the beginning. Once you do have your tasks, just take them off the queue and start running them, one at a time. Really, really, really simple. Once you've run the task, check your outstanding time. Like, did you advance the clock far enough to actually run a timer? If so, add that timer to the queue so you can actually have timers running at the same time as you're doing this. Otherwise, move forward and check your loop counter. If you have looped through this dispatch loop enough times, then instead of blocking on the kernel, what we're actually going to do, and I said this in the wrong order, but if you haven't looped through enough times, just go back to the beginning. If you have, pull the kernel. Like call that epoll wait function, but give it a timeout of 0. So it will just give you any outstanding events, but without actually blocking. And the results are you sort of move forward. This gives you the ability to get your I/O without actually blocking the thread if the thread is fully busy, like doing compute stuff or doing timers. And there you have it. This is actually how Node.js works. And this is actually very, very cool because it doesn't waste any threads at all. You're doing this with a single thread. Okay? It's not just an illusion. Like, Node.js really does only have a single thread. And it's actually really helpful. This pattern works really, really well when tasks are super small. Long-running tasks, by the way, just kind of delay the loop. They increase your I/O latency, but you can break them up into smaller tasks usually, and that kind of solves the problem. And it integrates timing and I/O into a singular thing. So again, like very, very efficient. You're not wasting separate event dispatch threads. You're not sort of bouncing your scheduler or something like that. Everything's great, except it doesn't support concurrency, right? Like you don't actually have true parallelism with Node.js because it's one thread. And libuv doesn't really give you an answer to this. So this is a really cool set of ideas, but maybe it's not really the final answer. So what would the final answer look like? Like what would the ideal look like on the JVM? Well, ideally, we would have threads which map perfectly one-to-one with processors. Okay, we've got a certain number of physical threads, maybe 8. We have that many worker threads, and that's all we do. And then we write logical tasks which, as much as possible, remain on one thread until complete, because threads generally remain on a single CPU until complete. So then we have like really nice cache affinity, like all that stuff. We need to represent an unbounded number of logical tasks because we might have like a network service with like many outstanding connections, but that's okay. Like we can kind of like figure our way to representing that. So the question is, can we do something like this? And I think the answer is yes. So basically, what if we were to take something like the libuv state machine that we had before and then just clone it? Like make a whole bunch of threads which do the libuv thing, and then whenever they are idle, so whenever they were about to block on the CPU, instead of just blocking, work steal between the threads. We already have these types of runtimes on the JVM where we do work stealing between worker threads and try to keep things very affine. Well, why not just extend this idea to something that integrates network I/O and timers? And if this diagram looks familiar, it really, really should, because it's the same technique that the kernel is using to schedule threads on CPUs. And in fact, each of these worker threads will be a thread on the underlying CPU. And this is actually really, really cool. And it gives us a lot of nice benefits, right? One of the biggest benefits being that these logical task time slices can be a lot larger than thread time slices. So that means our scheduler has like lower overhead, we have fewer context switch costs. User space scheduler can optimize for throughput rather than fairness because we don't have to worry about the sort of system entirely locking up. And you have this situation where like you basically do this by having one epoll file descriptor per thread, and then every time your logical tasks want to work with things, they just like register on that local epoll file descriptor. Again, what we're trying to get to here is a situation where our threads line up perfectly, and we have very, very few context switches. Ideally, all of this should be really, really invisible to users. Okay? So we should have a programming model on top of this which hides it away completely. All right, so I realize I'm about out of time, but I want to talk really super fast, like promise 2 more slides, about how close we actually are to getting this done, right? So today on the JVM, like what I just kind of gave you was like the pie in the sky ideal. How close are we to actually having this, and how can you get to it, like to kind of reap those tail latency benefits? Well, if you're using an effect system, then you're actually pretty close to this. So Cat's Effect, Zio, Tokyo, these are all really, really good systems that do a lot. Compute tasks are handled pretty close to optimally in these types of systems, like really, really close. Hard blocking tasks are kind of unfortunate, like file system I/O and things like that. They generally generate additional short-lived threads, but at least in Cat's Effect in Tokyo, the programming model incentivizes really small scoping around these things, so these threads can be very short-lived, get out of the way, stop doing as much contention. Unfortunately, this is where the good times stop, because even with modern effect systems, asynchronous I/O is still shunted to third-party libraries. So you use something like NIO2 or Netty, that creates these event dispatcher threads which then contend with the compute pool. You have timers that also do the same thing with scheduled executor service, and that's just not good. It really kind of blows away a lot of the efficiency and the optimizations that these systems are trying to do for you. That's if you're using an effect system. If you're not using an effect system, you're really out in the woods. Okay, so it's really, really difficult, right? Fixed thread pools are super common and really, really bad because they randomize worker thread assignment when you sort of schedule up tasks. Fork join pool is better a little bit in keeping things on threads, but it also allocates a ton of worker threads and like has all these problems with it. By the way, virtual threads that just landed in JDK 19 force you to use the fork join pool, so like everything is awful. And like I said kind of at the beginning, the state of the art on the JVM is to have these split libraries between async I/O and timers and concurrency. So this is not good. So what can we do? So really concretely, first, make sure you're using async I/O. Because I think at this point, this is kind of beyond debate that like using synchronous I/O is just really, really, really slow. Use an effect system if you can, okay? It doesn't matter which one. Forget about the holy wars. They're all better than nothing. They're really, really, really good, and they solve a lot of problems for you. And this is where the innovation will happen over the next couple of years. Align your active thread count to your physical threads, and take into account any heavily loaded event dispatchers. So if you've got an NIO2 worker, that's like one thread. If you've got a timer thread, count that. Minimize your event dispatch threads, and avoid using thread pools which speculatively over-provision workers. Okay, so thread pools like fork join pool or Zio's auto blocker, try to turn that stuff off because you really don't want to have that many threads floating around. So I'm out of time, but ultimately I hope this has kind of given you a picture of like where the future of this space is really going. It's trying to bring these things closer and closer together so we have really tight integration between concurrency and network I/O and timers because of the advantages that you see here, and the advantages that we get with really, really close integration with the way that the kernel and the hardware functions. So hopefully we have like a tiny bit of time for questions, and I haven't eaten too much of your break. Thank you.
I think let's have at least one time for at least one question. So.
Okay, thank you for the talk. My question is around like those ideal scenario for those threads. It feels like it's similar to how Golang have their Go routines implemented, would you agree with me? That's my first question. And second, do you think that Java is going in this direction, or perhaps there's even something better? What do you think?
Yeah, I would agree with you that what I'm basically describing is a coroutine runtime and a coroutine scheduler. And it ultimately comes back to the observation that user space schedulers are able to optimize more aggressively for application needs, right? I called it throughput over fairness, which is really what it is. You can have like these really long-running tasks, whereas the kernel scheduler has to be very fine-grained, and that's extremely inefficient. Another way of thinking about it is like a blocked fiber or a blocked green thread in Go or Cat's Effect is free. It just costs you a little bit of memory, but it doesn't cost anything else. A blocked thread in the kernel is very expensive. So yes, I think this is where things are going. And Project Loom actually pushes things in this direction at the cost of some other stuff. So like, this is kind of my premise, is like these systems like effect systems that really go this way are where the future is. Thank you.